Okay. So hi. So this is some work that I've been doing with Marcelo for a while. So I was interested in something else, which was understanding the semantics of reversible programming languages from a type theoretic point of view, and that led me to think about monoidal structures from a type theoretic point of view. And then I was talking with Marcelo, and he was also interested in something similar. And so then we thought about a bunch of things and proved a bunch of things. So I'm going to tell you about a few of those things. Okay, so so I'll just maybe say a few things about why this is important. So um, a few weeks ago, Eric Finster gave us a very nice talk about higher algebraic structures in type theory, which are useful for computer science. So just say higher algebraic structures. Um, so in type theory, so defining them is in type theory constructively with intentional equality. You have to think about a lot of different issues. So type theory comes with various tools like higher inductive types. Um, these higher inductive types can be different kinds, like recursive, non-recursive, and so on. And when you do them, you have to think about issues like coherence. So what sort of equalities do you add on your type so that the appropriate coherences are there? And you generally you're interested in proving that you have the right algebraic structure. So you think about the universal property. Um, so people have thought about these problems. For example, we can define notions of groups such as one groups, two groups, and higher groups in homotopy type theory. But groups tend to be easier because they have inverse elements, and since we are in groupoids, that's easier. So what about monoids? So let me tell you about monoids today. Um, the other interesting thing is that everything here is constructive. So I'm going to say constructive, but put some quotes around it. Well, because um, it is constructive if you think homotopy type theory is constructive, but strictly speaking, homotopy type theory doesn't have strict canonicity, and there are other issues to be sorted out. Um, so that's maybe a caveat. But um, anyway, so the thing is that it's constructive because we work with constructive equality. So whenever we think about equality, we have to use the tools of homotopy type theory to construct equalities, and we don't ignore any higher equalities. Okay, and so maybe why free algebraic structures are important in computer science. Well, free algebraic structures are in computer science, we study data structures. So for example, free monoids are lists, and free commutative monoids would be the data structure bag multisets, finite multisets. So if you can study them constructively, you can extract algorithms for computing for functions which compute with these data structures. And maybe sometime in the future, when cubical type theory takes over as the ultimate programming language, we can teach undergrads how to program with these data structures using cubical type theory. Okay, and maybe one other important point is that these data structures, we show that they, once we show that two things are isomorphic, in type theory we cannot distinguish between two things that are isomorphic. So there is this notion of representation independence, which means that if two abstract data types, if two data types have the same universal property, we cannot distinguish between them. So that's one important thing. And Okay, so yeah, so basically this is what what the applications I have in mind are, and um, and now let me just tell you about the main thing. Okay, so maybe I'll start with monoids. So there is a forgetful functor from monoids to sets. It has a left adjoint, which gives you the free monoid. Okay. So now we are in homotopy type series, so we can describe this free monoid. Uh, so we'll start with a very naive definition. So I want to describe F, which is a monoid on, which is a functor from sets to sets. Sorry, sets to monoids. Okay, so I'm using H sets here, which is the notion of sets in homotopy type theory. So I want to define this type f of A, where A is a set. I give the points. I'll say that it has. Okay, so I first. Okay, so I'm using the naive definition here. So I'll say first you include all the points in A. Okay, it should have a neutral element. It should have a multiplication. Okay, and it should satisfy the unit left law, which says that for all x, e dot x is equal to x, and the unit right and the associativity okay. And I'm of course working with sets here, so I will have to truncate. So these, so this is a type which I claim that this is a type. I claim that this is the free monoid on A. So these are the point constructors, and these are the path constructors. So how do I know that it's a free monoid? Well, this type comes with an induction principle, and using that, I can show that there is a isomorphism from Fa to any other monoid M. It's
Vikraman, that trunk, it should be is set Fa, right?
Oh, right. Oh, Fa. Yeah, so the universal property of the free monoid is the adjunction. So the type of monoid homomorphisms from f of A to M is isomorphic to the type of functions from A to the underlying set, and this is natural in A and N. Okay, so this is not very hard to prove. You just use the induction principle to show this. Well, okay, now this is a very complicated type. We added lots of equations, and it's a complicated higher inductive type. But of course, we know that there is a better description of the free monoid. Classically, we know that it's just the sequences of elements drawn from A. So we can describe it much in a much simpler way using lists. So lists have the nil, the empty list, and okay, I'll write this. Okay, so this thing doesn't have any equations. It's just a 2-point constructor. So it's a recursive type or an inductive type, and it's easy to use. And so what is the so this list is a monoid where the append operation, let's say plus is defined. So when the list is empty, it's ys, and if it's x, I'll just use the dot for the commas. Go to x dot x as plus ys. Okay, and this append operation satisfies the unit law. So nil plus ys is equal to ys, and the unit right, the associativity law. So now this list is from type to type, but I'm just thinking of sets, so I would truncate it to sets, and so this gives me the free monoid on sets. So we have to show that it's the free monoid again. So this time we need a okay. So the type of monoid homomorphisms from list of 8 is equivalent to yeah. So I'll stop writing the U because that's just the underlying set. So if I'm given something like this, what you do is just compose with cons blank comma nil, which is just inserting the A into the list. I'll just call this eta. And if you have this given a function from A to M, I can uniquely extend it to a function from list A to N. So I'll call this F sharp. So how do we show this? Well, it's just list. So we construct this F sharp. When it's nil, we go to the empty element, and when it's x dot xs, we go to f of x, and then multiply in the monoid with f sharp xs. And then it should be so we have to show that this operation is an equivalence. You have to give homotopy, so f sharp compose eta should be homotopic to f, and this h compose eta after extending should be homotopic to h. So again, these are followed by simple calculation. Okay. So now what if we go to commutative monoids? Okay, so the same, we can try the same naive way of defining commutative monoids. So we define f of a. We say that it has the eta, which goes from a to f of a, and neutral element, and multiplication. Okay, and then the unit law, associative, and the commutative law, which does that for all xy. Say x dot y equals y dot x, and truncate. Okay, and okay, well, the universal property says that commutative monoid f of a comma m for m any other commutative monoid is the same as a to m. Okay, well, okay, so now this is the same thing as f of a for monoids, but is there a different description of it such that we don't have to write so many equations? Well, we can start thinking about taking the definition of lists and maybe quotienting out with some equivalence relation, which says that you can take any permutation on the list of elements, and two lists are equal if the elements are permuted. So it turns out to be difficult to describe permutations because you need to describe what a complete set of bijections are, and so we don't want to think about that because that's difficult to do, and unless you run into issues like having to require decidable equality on A and so on, and we want to do it more generally for sets. So so what we can do is this so permutations are generated by swaps, right? So sequences of swaps. So in homotopy type theories, so because of recursive higher inductive types, we can generate these permutations along with the points. So here is a different description of this, which is I define this type MA, which has a nil. And I add a path swap, which says that for all x, for all y, for all xs, cons x, cons y, xs is equal to. So it just swaps the first two elements, and then I say I truncate this to sets. Okay. So now my claim is that this is also the free commutative monoid. So we will have to prove it. So this is a type. Let's try to write down the induction principle. So the induction principle says that if I have a type family P over NA, and it comes with the following data, which is that nil star is nil. Const star says that for all x, for all xs, I get something from P of xs to P of x dot xs. Okay, then there's a swap which says that for all x, for all y, for all xs, if I have a P, if I have something, if I have a P xs, let's call it small p. Then I can take cons star of x comma xs comma p, and this is equal to cons star of y. Okay, sorry, there is one more cons here. Okay, something like this, but this equality is not right yet. We have to do a transport over the swap of x, y, xs. Okay, and we also need to make sure that for every xs, the fiber is a set. Okay, so given all this data, there is a unique function f from xs a to p of xs, which satisfies the appropriate computation rules on each. Okay, so I mean, I want to write down this because it's very complicated. So using this in practice in a type theory that doesn't know how to handle higher paths, you have to do a lot of work to use this induction principle. So my claim is that this is very hard to use, and we have to find a better universal property instead of using this induction principle. So for one thing is that if this if you know that this type family is a proposition, P is prop. So for all x's, if you know that P of x's is a proposition, then we just need two pieces of data, and from this we can get a unique function f prop P of xs. So you can prove this from the previous induction principle. It's just that since everything is a prop, we can fill in the square for swap freely. And it turns out that most of the things that I'll be proving with M of A, they turn out to be props. So I can use the simpler induction principle, which basically works just like lists. Okay. And then finally, I want to prove the actual universal property. So first, I want to show that M of A is a commutative monoid. Okay, so all the laws of commutative monoid are propositions, so I can use this universal property. So the usual ones, which is the unit law and the associative law, these would follow from the same thing that we did for lists. Of course, yeah, I did not define the multiplication yet. So multiplication works just like lists. Nil ys minus extra x's comma ys. And this is not enough because this is a set, so we have to show that this is invariant under swap. Well, it turns out it's very simple because you just do x dot y dot xs, and then you apply the swap on these two and turn this into xs plus ys. Okay, so this part is easy. Well, okay, we have to still show that it's a commutative monoid.
Can I ask a question? Right?
Yeah.
So with this style of working with free commutative monoid, I mean, you have to work with this quotient, but couldn't you just like count the number of elements that the number of times that you have each thing? Wouldn't that be more direct? It seems like you're not using the most direct type to.
So you mean
making your job unnecessarily harder. Maybe there's some reason you couldn't do the sort of trick like that.
Okay, sure. So I mean, to count the number of elements, you would need to use
They count the number of times each.
Yeah. So you would need to use equality on the
alphabet.
Oh, it's dropping out. Yeah, I was saying that to count the number of elements, you have to use decidable equality on the underlying set. Hello.
And you want to avoid doing that. Why do you want to avoid that?
Yes.
I guess I'm not sure what ultimately applications you have in mind of these ideas.
Yes, I mean, I'm doing it for sets, but my goal is to generalize it to higher dimensions. So I don't really want to just think about sets and decidable equality, because that's just zero dimensional.
Okay.
Yes. Okay, and
so maybe one thing that there's a classical theorem that says that if you do have a decidable equality, then you're necessarily a set. So I don't know if Jamie is. Maybe that's one. So yeah. So in other words, so if you work with a decidable equality, then you're automatically keeping yourself from being able to generalize it to higher dimensions. It won't work. So
okay.
Maybe that's.
But these are just regular monoids, right? They aren't infinity algebras or something like that.
I mean, here he's looking for the free infinity.
Vikraman.
E-infinity algebra on the time.
Yes. Yeah. So yeah, right now I'm just truncating the sets, but I'll maybe mention that I'm going to go into higher groupoids towards the end. Yeah.
Okay.
So if it was infinity, it would be E-infinity algebras. Yeah.
And while we're chipping in with questions, I got one as well. So when you defined M of A, you chucked in a trunk axiom, but you didn't need to do that with list of A.
Yeah.
But am I right in thinking you still, it's not completely immediate that if A is an H set, then list of A is an H set. You actually have to prove
you
that.
have to prove it. Yeah.
Yeah.
Because I mean, the reason is that I'm adding this swap, which is going to generate higher paths. And I want to truncate them if I want to be in H set.
So I have to go and get my children from school in a few moments. Eric has kindly offered to continue as chairperson after I leave. So anyway, please carry on, Vikraman.
Right. Okay, so and maybe I want to say it, so it's commutative monoid. So you want to prove that this append is commutative. So it's commutative. So for all x's, y's. Okay. So here you have to do some work actually. So it turns out that what you need is to show that you can recursively apply the swap to move around the elements of the list. So you need a lemma, which is like this, which is that for all x, for all xs, x dot xs, this is the tiny dot. This becomes xs dot the singleton. So we can recursively apply the swap to move this x to the end of the list, and using these two lemmas, you get the commutativity of. Sorry, using this lemma, you get the fact that this append is commutative. So this is a commutative monoid, and then I want to prove the universal property. So this is if I have an f from a to m, for m any other commutative monoid, so I can go from a to m. I'm going to call this f sharp, where this is the unit of my monad. Yeah, and again, this f sharp is defined by induction on m of a. Again, on the point constructors, you do it just like lists, and on the path constructor, you have to use the commutativity of m, and so on. So yeah, so this satisfies the universal property. So now we have two different descriptions. One was f of a and m of a. They satisfy the same universal property, so they're equal. So I'm going to give another description of the free commutative monad. I'll call this n of a. So this comes from. So let's try to understand when are two free commutative monoids equal. Well, let's think of these lists. If I have two lists like this, and I want to understand when they're equal, well, they could be equal pointwise. There's a equals b and as equals bs, or there could be I could swap the a and move it somewhere inside bs. So it could be like a followed by a b somewhere and a cs. Okay, so I'll just this kind of thing. So if you start thinking about this, you can write a different path constructor, which is so n of a is another commutative monoid, which is again nil and cons, appropriate type, and there is a path which commutes like this. So it says that for all a, as, b, bs, cs, if you have a path which goes, so we have as equals b dot cs, and es equals a dot cs, then we can say a dot as equals b dot s, and of course the truncation. Okay, so now this is another description, and I claim that this is also universal. So this is maybe a theorem. N of a is a free monoid. Okay, so now we have three different descriptions of the free commutative monoid, and we can show that they satisfy the universal property. So now, so I'm going to use them to do some calculations, which are quite interesting. So the point is that all of these calculations can be done extremely formally. We just need to use the universal property. Okay, so I'm going to build the relational model of linear logic, just intuitionistic propositional linear logic. So so note that H set is set, and M is the free commutative monad on H set. There is also the power set monad on H set. So how would we do this in type theory? Well, type theory is not impredicative. It is so we could define the power set like this. X maps to H prop to the X. Okay. Now there's a slight problem. It's because H prop is not exactly how you think of the subobject classifier. So it would go from I to I plus 1, and you have to use a propositional resizing axiom to put it back in the same I. So power set, you don't exactly get the power set monad, but we can avoid the resizing axiom and still use this power set by thinking of it as a relative monad. So okay, so so we can prove the properties of relative monads like this. So first is the unit of my power set monad. So this is my unida. So it goes from X to power set X. This X maps to lambda Y. X equals Y. Okay, this is my unit. And then I have the extension operation, which is that if I have A to power set of B, it goes power set A to power set B. Okay, so this would be given by so lambda X dot lambda B. There exists A such that F A comma B and X A. And so this is a Kleisli extension, and I guess so. Yeah, they satisfy some laws. And how much time do I have? Okay. Okay. So there are some interesting facts about this relative monad. So when you try to prove the associativity law for this, you actually have to use function extensionality and univalence, and then you end up having to show a codensity lemma for this. And
so Vikraman, could you give a bit more context? I mean, why do you want to build this relational model in this way? I feel that was helpful.
Yeah. Yes. So my claim is that if you just have the universal property and a few formal structural rules of this power set monad, you can build the whole relational model completely abstractly.
So ordinarily that we would build this model concretely, right? I mean, it's
concretely,
not
yeah.
model.
Yeah, just thinking about multisets and power sets, yeah.
Sure. So what are the advantages? Maybe I'm asking the question because there are too many. But what particularly is motivating you to construct this in this way? There's all sorts of things in mathematics we could try to construct in these sort of.
Yeah, I think the claim I'm making is that,
I'm just asking about the big picture of this program, right? So you're not doing this because there's some big problem with the relational model of linear logic, which homotopy type theory is going to solve.
Yeah, right.
I'm asking for the big picture of your motivation, and just to expand on that a bit, if you can.
Yes. So, I mean, I just described 3 different ways of constructing the free commutative monoid. So if I had to construct the relational model using one of these, then, that would be too concrete, and I would have to do it separately each time. But, if I could just use the universal property and prove it, I could change out my representation of the free commutative monoid and switch to something else. Yeah. And of course, I mean, the other reason is that I'm doing this in type theory, so it's automatically coherent up to higher dimensions. So I can, instead of talking about 8 sets, I could move to groupoids, and then I would have a relational model in groupoids, which has more structure than the one in sets. Okay. Okay, so maybe I'll just summarize instead of going through everything. So usually the relational model is given like using a distributive law. Since the power set monad here is a relative monad, we don't exactly get the distributive law, so we have to do a few tricks. So so we consider, so first let's define this category of relations, but I'll call it HREL. So here the objects are H sets, and the morphisms are relations. And well, normally we know the rel is a compact closed category, and we can also do this here, but we would have to do everything in type theory constructively. So it has a tensor product, right? So the tensor product is given by product of the underlying sets. It also has a lolly, or a linear arrow, which is also given by this, and we can show that HREL x comma y z is shown. Okay, and this makes it a symmetric monadal closed category. And on this HREL, I can then lift the free commutative monoid monad. And there's the trick is that you can do it completely formally. That's what I was trying to say. So this becomes a linear exponential comonad. If I mean, let me just maybe try to show this. So we want relation from M of 8A, but we could do it like this. So we've got A to M of A, which is my eta, but I can go to long set of A using the eta, and then I can extend this along eta. So yeah, and then it has M. Okay, and it satisfies the axioms of the linear exponential, and in particular, you also have this CD isomorphism, which is that it turns sums into products. It's a strong monadal functor between the plus and the times. So, and there is also a way to derive this just using the universal property. Yeah, and so this basically gives us the relational model, which is the degenerate model, because the tensor and the power coincide. And now let me tell you one more thing, which is we can take the co-Presley category of this. So this would be the construction of the category of generalized species, but only for sets. So here the objects are sets, but the morphisms are like this. Now this category has a lot of structure, and we can also show this. So you can take the product. This is given by A plus B, the coproduct of the underlying sets. And it also has an exponential, which is given by NA times B. And you can show that this category is Cartesian closed. Not only that, it's also a Cartesian differential category. So differential categories were invented to give semantics for differential linear logic. This category that we have, it also satisfies the axioms of a differential category. And the reason I introduced three different ways of representing the free commutative monoid is so that I could get one of the axioms here. So so let me just say a few things maybe. So if I have, let's say, f and g from A to B. They have an addition, so you can take this is defined pointwise. There is also a multiplication. Okay, this multiplication isn't pointwise, it's given by deconvolution. So have to do alpha 1 comma alpha 2 such that alpha equals alpha 1 to alpha 2 and alpha 1 B to G alpha 2 comma B. Okay, so what so this is this addition and multiplication satisfy commutative ring structure, and so this category is enriched over commutative rings. Now further, this has a differential structure. So it says that if I have an f from A to B, I can differentiate the f, and I could get I could turn it into a linear function. Okay, so this is okay. So by definition, this is MA relation A comma B, and I mean, okay, so this is now in relations, so we can write A times B. Okay, so let me just show you how to derive this. So this would be given. So take an alpha A comma B and map it to f of alpha dot A comma. Okay, now this differential it satisfies the Leibniz rule. So the Leibniz rule is so let me fix an A, then I have del f A dot G A okay, so I mean, okay, this is one of the axioms of a Cartesian differential category, and well, now we want to prove this for our H of M that we constructed. But okay, if you expand out the definition, you will see that you have to prove an equality like this, which is that alpha dot A equals okay, and you have to show that it's equal to there exists beta such that just alpha, okay, and alpha 2 alpha 2 or alpha 2 beta equals alpha and beta from Okay. Okay, so now the point I'm trying to make is that this equation, it follows from the paths in N of A. So we have to go back to our definition of free commutative monoid, and then we can use the paths in A to just construct this equality. And well, yeah, so that is how we get the Leibniz rule. And in fact, there's also the chain rule and so on. So indeed, this gives you a model of differential linear logic. And yeah. Okay, so maybe I'll stop there and just mention a few words about groupoids. So this M of A that I constructed, this was on H set. Okay, but we could also move to groupoids. So when you do it for groupoids, you have a nil icons. And swap, which says x dot y dot xs plus y dot x dot xs. Okay, so now we can't truncate at sets, okay, but we'll truncate at one groupoid. Okay, so we have to add two higher paths for this. Okay, so the first one you want to add is that x, y, xs. If you swap x, y, and then swap y, x, xs, this is equal to ID. I'm not writing it properly here because I'll just use composition in case. Okay. And this isn't enough. You have to add a hexagon, which says that if I take three things, I can do the first two. So I started by doing x, y, and yx, and then I did these two, and these two. Okay, or I could do x dot z dot y dot xs, z dot x dot y dot xs, and that's it. So you have to add a filler for this thing, and this huge high inductive type will give you the free symmetric monoidal groupoid on A. And then you can repeat all the constructions that I did, but instead of thinking about just commutative monoid homomorphisms, you think about symmetric monoidal functors between groupoids, and you generalize to one dimension higher. Right, I haven't finished checking everything in this construction with groupoids, and that's what I'm doing now. And okay, the hope is that we could go to some higher groupoid sometime in the future. Probably if you go to infinity, the E infinity space has some of those. And then the point is that all the constructions that I did, they don't rely on the representation of the groupoid, just on the universal properties. So you could repeat all these constructions and give a higher dimensional version of the constructions. So yeah, maybe I'll stop here, and if there are questions.
Okay, thanks very much. Should we give the speaker a quick round of applause? Yeah. Thank you very much. And so I guess just unmute yourself and chime in if you have a question. Any questions?
Vikraman, could you put back the slide near the beginning where you've got the definition of n? You had three ways of building the.
Yeah, it's this. Yeah.
Yeah. So the interesting thing about that is that so that's not as it were, an algebraic theory. It's an essentially algebraic theory.
Yeah, it's a
because you've got conditional equation there.
Yeah.
But nevertheless, I suppose if I wanted to play with that, I suppose cubical Agda would allow me to do that, wouldn't it?
Yes.
It wouldn't barf at all at having a conditional equation or thing.
No, it allows you to define this, and I have it defined, and I did prove things with it. Yeah.
Yeah.
So I don't know any other conditional hits like this. This is the only one that we used here that I know of.
Yeah, it's a nice example of why you might want to consider them. Yeah.
Yeah.
If I could follow up on one of Jamie's earlier questions. So if we have some type X and we define, or we look at the function space X into N, where N is the natural numbers, we certainly don't need to require any assumptions on equality here. So you're saying this won't have the right universal property to be the free commutative monoid, even though for sets it is. Does something go wrong? Or where does something go wrong if you just look at this type? And
okay, this is
you need to cut down to the finite support, right?
Yeah, so functions with finite support, so you do like x to the n, but this is just list, so you'd have to cut down by symmetries of permutations on n. But proving the universal property from this is quite difficult.
But you could take a different type rather than n, right? You could take the union of the classifying spaces of the symmetric groups.
Oh, okay.
And then that would take care. Then that would take care of the symmetries for you, I think, right? Like
okay,
there's there's the big way to say it, where it will jump at universe level, which is it's the sum over all finite sets with a finite set mapping to x. Instead of n, you take the universe of finite sets.
Okay, so the universe of like u fin.
Yeah.
Column n x equals fin n, like this.
Right.
Okay, and then I could define x isn't something u fin.
And then right. Well, okay, so maybe a or something like this.
Okay, right. So this is, and then x to the a.
Yeah.
Oh, okay. So this would now okay. So if you want to prove the universal property, we would have to reason about fin.
Yeah.
Permutations on fin. Yeah.
Right, and so univalence will tell you it has the right paths because the symmetric group actions.
Right.
I mean that is true, but that does not mean. So let me. That is true, but it doesn't mean that you can automatically prove a Leibniz rule, for instance.
No.
Yeah.
That's the main point. That
Sure.
you need.
We still need the n of a
exactly
to do something like Leibniz rule.
I'm just saying, but you can, instead of taking the quotient, you can do this, and then you don't have a quotient. You get the right thing, so you don't have to describe the quotient or whatever. But it's true that you have a lot of more work to prove if you want the correct.
That's right. Then you cannot prove what you want to prove.
Yeah.
Yeah.
Anyway, yeah.
Can I follow up with one clarifying question? So you're using the concrete representation of n to prove something. Does that mean you can't prove it just using the universal property of the free commutative monoid?
The differential, no, it doesn't just hold for from the universal property of free commutative monoid.
Wait, at all, or it's not easy to see how to prove it using the universal property?
I don't think it is possible.
I don't know any other proof of the Leibniz rule without going through this different representation.
Yeah.
Right, okay.
And in fact, the representation was motivated from the fact that one wanted to prove the Leibniz rule.
Yeah.
And it's related to some other things in differentiation, like creation annihilation operators. So there is a basis for this. It's not coming from nowhere, but it was really in trying to prove the Leibniz rule that one is led to consider this conditional inductive type.
Also, just one question on when you do the relational model, you ask your relations to take values in prop.
Yeah.
But is that necessary for?
Yeah, no, I was just doing the zero-dimensional one, but we could go to groupoids and go to H set.
I guess I was just trying to
okay.
figure out what things go through here if you lift that condition that the relation is.
Yeah, I could take from X to U, so like presheaves.
Yeah.
And this, yeah, I did most of this using presheaves and then just switched to H prop at some point.
Yeah, so that's what I was wondering is which equation does the coherence force you to use H prop for this to work?
Well, I mean, one thing is that, if I did it for arbitrary U, then what are the axioms for a monad? So this. These are set valued, so I'm just using on sets.
Right.
So.
Right. Well,
Yeah.
I mean, so right. Okay. I mean, so do you use the fact that this monad satisfies a bunch of laws to prove?
Yeah, I'm using the Kleisli bicategory framework, so I'm just using the Kleisli triple laws.
Okay. Okay. Yeah. So I agree that would be a bit of a problem.
Yeah.
Okay.
Can I ask a couple of questions about the start?
Yeah.
So if you go back to your original higher inductive type of a monoid, I don't know if you've actually tried to work with this, but do you find you run into problems if you ever want to try and define a map from this monoid to something that isn't a H set? Because you have this truncation axiom.
Yeah, you can only eliminate H set. Yeah.
So, but then on the other hand, if you've got lists, it's fine to define map some lists to like any type. So is there, I guess what I'm getting at, is there some way you can do this as a higher inductive type but without sort of sabotaging your way of being able to map out of sets?
Okay, so just for monoids, well, no, if we started doing it like this, then we would have to figure out what are the
you'd have to figure out all the coherence conditions.
What the coherences for the higher monoids. So yeah, the fact that we can write it as a list, it means that lists are probably have the right coherences at every dimension because they don't have any equations. But we can't do it for commutative monoids.
So you don't know any way to do something similar for commutative monoids that doesn't have a massive truncation axiom stacked on top of it?
Yeah, so if there was a way to not truncate, there might be some trick with finite types, fin.
I think this gives the right answer, but like Marcelo was saying, it's not necessarily, it doesn't give a description of the universal property it's supposed to satisfy. So
yeah,
you can't compare it with anything, even though it's the sort of right underlying type.
Okay. And I had a sort of another further question is that in some of the later stuff I've worked with doing, so instead of using lists, I've worked with using functions from the base set to the base set. Can you do something similar here, or does something break down with what you're trying to do? Or so like using functions with composition instead of lists with concatenation?
To do what exactly?
To build up this type. So you're making the free monoid by functions from the base set to the base set with some condition on it. And I think if you do this correctly, you'll get associativity and unitality for free.
So the free monad, but I take functions from A to A?
Possibly with some extra propositional value condition on this. I'm not sure
Okay.
now that but maybe I have to go back and think about it.
Okay, I don't know about this, but
It definitely works for groups, but I'm not sure if it works for monoids.
Okay, well, there are other different ways of doing groups as well, free hire groups, but that trick doesn't work for monads.
Okay. Thank you.
Any other questions? Okay, then we'll thank our speaker again. Thank you very much. Okay.
It's asking me to stop the recording. Should I?